efficiently. All right, so classical electrodynamics, boring. It's a dead subject because it really essentially has not changed in the last 100 years. And perhaps for you most personally, you've studied it before and you feel you know everything already. There are, quite frankly, much more interesting forces in nature. Yeah, certainly in terms of you know, maybe impact on cosmological timescales, but just in terms of also other things that you know, the nuclear forces, they're kind of you know, different beasts on this. Essentially, one of the very charming things about electrodynamics is, of course, its history. And its history actually goes back a long, long way, all the way to the Greeks, who kind of first understood, well, they didn't understand, but first observed some strange things like magnetite and things like that, but they didn't understand anything. In fact, it's quite surprising to go back just, you know, like 250 years and notice that people really didn't understand anything about electricity and magnetism at that point. You know, they had some ideas about stuff, but it was extremely basic. And then there was this explosion of understanding in the next approximately 100 years based on that, that really made a towering achievement of like physics, possibly incomparable with all other achievements in physics, including those of the modern age. So yeah, the fun things about electricity, people understood at some point that this had something to do with biology. There are these really interesting experiments of Galvani that you can read about involving frogs. Frogs have a particularly difficult relationship with electrodynamicists throughout history. We'll see more examples of this. And you know, it started with frogs, but also they kind of went further to more macabre situations. In Italy in those days, I don't know, maybe there was like a thirst for revolution or blood back then, but anyway, so they did lots of stuff. Interesting conclusion, indeed, we work with electricity. Then here in the Netherlands on Friday afternoons in Nijmegen, the group of André Geim and Luciano Voselov, they were doing lots of interesting stuff about other things like graphene, but they were also exploring things. And there's this nice little movie. I don't think I've got the movie here. You can find it easily on the web, where they just used one of their ultra strong magnets in the lab and they just levitate the frog, and you see the frog like dancing in space, wondering what. Yeah, so it's a very fun thing. And so this guy André Geim was in the Netherlands until I think they didn't promote him in Nijmegen, and then he buggered off to Manchester, and then he won a Nobel Prize later. Of course, in the Netherlands, we're all very happy that there was some Dutch person winning a Nobel Prize, but they hushed completely the fact that they haven't given him that job. Therefore, he had left. Yeah, so that was very unfortunate. But maybe you know André Geim already. So what's the main characteristic of André Geim? What distinguishes him from all physicist people? He won 2 prizes. Yeah, so he won the Nobel Prize, of course, but he also won the Ig Nobel Prize for that particular research. Okay, so that was interesting, and we'll understand those things later when we discuss the interaction of magnetic fields with matter. Okay, so electrodynamics, yeah, used in culture as well. It can give life. Perhaps more impactful in history has been that it can also give death. You think this is a nuclear bomb, okay? However, it is not. It is an electromagnetic bomb. It is electromagnetic because the reason why things blow up is electromagnetic. It's not the nuclear forces that propel things away from another. The nuclear forces, they just take a big chunk of nucleus, they split it in 2 like that, and that's it. They've done their work now. So there's no heat, there's no explosion, there's nothing there. There's just a heck of a lot of electrostatic potential energy. Okay? And it's when the nuclei, the 2 fission products, fly apart because of electromagnetic forces that you end up having heat created there, transfer to, you know, the environment around, and just the big cacophony that you all know about. So this is all just Coulomb's law, really. You got to do relativistic things because the nuclei fly off at about 3% the speed of light in this. But once you know how to do relativistic, like classical electrodynamics, you know how to compute these things. Okay, there are extremely profound aspects of electric charges and classical electrodynamics that remain to this day ununderstood, despite everything you might read. There are experimental facts that are, up to this point, undeniable, but they are experimental facts. This is not theory. What are the facts that we see? Charge comes in two different varieties, plus and minus. This is already a bit bizarre because we can think of gravity and there's no plus and minus in gravity. They both have a force that has the same kind of decay in space, 1/r², but one is like completely different than the other. So electrostatics is a bit like gravity, but with two different types of masses. Strange. Even stranger, the charges that you can find are multiples of a fundamental unit, okay, that recently was understood to be splittable in thirds, but no further. So the electron's charge is a unit. It's the same for absolutely every single electron ever interrogated on this. What's your charge? What's your charge? This. Same thing, okay, to arbitrary digits that we, as far as we know. More strangely, the value of the charge of the positive particles, proton, for example, is exactly the same value with a different sign. Why? Okay, unanswered. Another kind of more elaborate thing is that charge is conserved locally. You will not have spontaneous appearance or disappearance of charge if it violates a kind of sum rule that says that the local summation of all charges is a constant. Okay, it varies according to a continuity equation that we'll see, but it is conserved, and you'll see mathematically what it means when we present the continuity equation. Okay, and then the other experimental fact that you have is that the force has an inverse square form. Okay, again, this is not something that you read in the Bible. Okay, it comes from experimental observations, then dressed up with kind of theoretical pseudo understanding. But things could be different. Mathematics does not dictate these forms. Experiment dictates these forms. And I say this as a theorist. Okay, and perhaps one of the more incredible things about this is that these forces display a principle of linear superposition. That means that if you compute the forces independently from each other, and then you bring other things in play, you haven't changed what's already there. I don't know if you've ever thought profoundly about what that means and whether that applies in your daily life or not. But if you do, you will see how strange this is. If you think of any other force, I don't know, let's say you've got a water hose, okay? And you're trying to push a ball with the water or something. Fine, then you measure something, you measure some force that you can transfer into the water. Somebody else comes with a different hose, and they start doing the same thing as well. Now, the two jets of water interact with each other, which means that the forces don't add up. Okay? So you can't measure one force from one jet, one force from another jet, and then put the two jets together and measure the sum of the forces. It's nonlinear. The world is nonlinear. Everything around is nonlinear. It's just the way it is. Complicated stuff is nonlinear. But this is absolutely purely linear. Okay? It means that irrespective of the intensity of a light field, you can still shine another light field through it, and this new light field is not going to feel anything about the existing light field. Okay? Interestingly, if you go very deep into quantum effects, you will be able to find a process that effectively scatters photons on photons. But this is quantum. So the only nonlinearities in that are quantum. Okay. So maybe a little walk through history, things that you really should know. I mean, you're not going to be examined on, but you should know about it. So Millikan. Does everybody know Millikan's experiment? Yes, no? Okay. So in short, essentially, Millikan is the one who did kind of fundamental experiment showing that charge is quantized. And how did that work? So it was kind of a complicated setup. He had a little spray that was creating tiny droplets of oil that he could then give charge to using some I don't know if it was X-rays or some radiation, was able to put charge on these things. But the point is that these droplets had a very controllable size. They could actually calculate the size of the droplets by measuring the time it took to disperse through a medium, because the mass of the droplet goes with the radius of the droplet cubed, but the friction force goes with the square of it. And therefore, if you just measure the drifting time of these, you get an idea of the size and therefore the mass of the droplet. Okay? And then you put two plates with an electrostatic potential. And you've got the droplets coming into there, and you're trying to capture them by an electrostatic field, trying to give an upwards force to your droplets. At some point, the droplets are going to float. They're going to float because the gravitational force is going to be exactly canceled by the electrostatic force. Okay? But what you see is that the drops, they kind of get quantized. So if you can only float the droplets if your field is of certain values, not at anything. Okay? So he was able to determine the fundamental charge of the electron to an accuracy of he published 0.5%. This has been contested a little bit. They say that if you put all his data together, it would be more like 2%. Let's give him 1%. It was still good enough. Okay. And I think there are still experiments of this sort that are running, trying to improve this. But we'll get back later to the actual measurement of the fundamental charge here. Okay. So in fact, we're going to do this right now. So you might think that this Millikan idea is superb, because what it does really is create isolated instances of effectively singly charged particles, like an extra electron in there. 1, not 2, not 0.5, not pi, 1. Okay. So, however, today the most accurate way of measuring the fundamental charge of a single elementary particle involves two experiments using bulk dirty junk from condensed matter. Okay. When I started in physics, I wanted to be an astrophysicist. Yeah, that was cool. I went into it. I thought this was great. But then I kind of did it, and I thought, yeah, this is really all done. There's a lot of exciting stuff, but there's more exciting stuff on the side and whatnot. And then I drifted from one place to the other until I landed in condensed matter physics, because this is where the wild stuff really happens. And it's great because you all think it's boring. Therefore, we can have a little secret society where we do all these tricks there that nobody knows about, nobody understands, that gives them mobile phones, that gives them all the technology they use, for which they are immensely thankless. Yeah, but that's the cool stuff in there. So let me present you two cool things. Again, coming from condensed matter. There's a thing called the Josephson effect. Brian Josephson was a young student in his 20s when he came up with the following idea. Let me take one superconductor, let me take a different superconductor, let me put a thin layer of like junk in between, and let me stack that up. And then let me put a voltage on this. What are you doing? Okay. Well, what he's doing is creating a device that has a very, very, controllable frequency of oscillating current. You measure a current going back and forth between these two things when you put a voltage. And the amazing thing is that the frequency of this oscillation is a ratio of two fundamental constants, Planck's constant and the fundamental electronic charge, h bar over E. Okay? You can measure that in the lab, and you're going to get h bar over E. So you go to a different lab, different setup, two superconductors. They also measure h bar over E. Yeah, 1 E, not 10 E. Okay, and it's not sensitive to the junk in your setup. That's the frequency. It's a fundamental thing with these phases of matter. And then there's another. Ironically, the fun thing about the Josephson effect is that it was thought out by Josephson theoretically. Okay, this was not like independently discovered. This was thought out. Like the transistor It was invented in the head of a theorist, which gives us hope as theorists. Yeah, also challenges to do the same. The other effect, which is absolutely remarkable, is the quantum Hall effect. So who among you had heard of either Josephson or Hall effects? Very good, very good. Okay, so they explained a bit where it comes from, right? So what do? You take a two-dimensional material able to transport electrons, badly, but still a little bit. You put it in a perpendicular magnetic field, and you measure the kind of transverse conductivity or resistivity, equivalent. And what do you realize? Well, it's that if you do measure the resistivity at very low temperature in these things, it comes in multiples of units, fundamental units, which again involve a combination of fundamental charges. So now it's E squared over H that gives you the conductivity. But before you had E over H, right? So that's it. You just put these two measurements together and you have the most accurate determination of the charge of a single electron. Let me emphasize the miracle here. We are doing two experiments which require junk. They require bulk, 10 to the 23 particle. Maybe they do it with 10 to the 21 small devices. But macroscopic junk devices give you the most accurate determination of the fundamental units of charge. Okay? It's an absolutely miraculous thing. So you might have thought that Millikan showed the way to do it. Just isolate your electron and then try to measure its charge. But this is absolutely incapable of competing with this kind of junk, useful junk that comes from condensed matter. Okay, so this is like quite miraculous. And I'm happy you've seen the thing. Okay, so let's ask the question. There's one absolute value are missing on the left. HTML. But, anyway, so let's now ask another question. So how accurately is this charge quantized? Because, okay, we've done some experiments that give us this, but at the moment, it's really a question whether everybody has the same charge, everybody at least in the community of electrons. So there are results on this using a variety of different experiments here that give an accuracy. Usually you talk about 16-digit accuracy for quantum electrodynamics and that sort of thing. This kind of study here goes down much deeper. Okay, so 10 to the minus 28, you're kind of really probing almost the double precision on your computer. Yeah, so these days, what you do is that you take atoms and you cool them immensely until they develop some kind of quantum coherent states that are very robust because they involve many particles together, but they still have some time-dependent oscillations in them. These oscillations are sensitive to the value of the charge because there's a coupling to a magnetic field. And by being extremely careful with what you do here, what you can do is construct some of these setups where these oscillations can interfere with each other. And then it's by measuring the interference pattern of these things that you can ascertain whether things oscillate synchronously or with a little bit of dephasing. Okay, so what I'm telling you here is that this is pushing technology to places where nothing else on Earth is able to do these things. Right? There's a lot of activity in people trying to use the very latest developments, be that in condensed matter, and called it in atomic physics, optical physics, in order to go back to these fundamental questions and try to push our understanding of these things. Why? Because one day, hopefully, in a sense, somebody will find that there's something wrong. They say, no, look here, systematically here, if we put the electrons in that kind of setup here, we measure that charge. If we do it this other way here, we measure that slightly different charge. And here, reproducible. You see, there is a difference. It just happens to be in the 60th digit. Okay? So if that happens one day, we have to rewrite a lot of stuff. And if it doesn't happen, then we just push and push and push and push. And we still don't understand why it's like that. We just see that it is. Okay? So that's one thing. Now let's go back to a simpler question. The very starting point of the course is Coulomb's law. And I, for one, am extremely resentful of the accidents of history that name things according to certain people. And Coulomb's law is one of my pet peeves. It is not Coulomb, okay? Maybe Coulomb was on Twitter back then and managed to claim for himself stuff that other people had long understood, okay? But we'll get back to this. So is there a deviation? Is the law for the force really exactly 1 over r squared, or is it 2.00001? Right? Or is it maybe something that decays exponentially with distance, like you would get if photons had a mass? In fact, this form that you have here, exponential minus inverse, like reaching length r divided by r, is much more natural. It's the kind of potential that you get, the kind of effective potential that you get in many, many other fields of physics. But the photon seems to have 0 mass, and therefore it's really 1 over r squared for the force. But this again is experimental fact. There are many people before Coulomb that actually did the work, and I want to highlight one particular, which is Henry Cavendish. Yeah. I was born like probably 300 years too late. I would have loved to be Cavendish's friend. He had a few intricacies about himself. He was an extremely shy person. He would only talk to one person at a time, not two. Who was like in Cambridge back then doing his experiments. And the great thing about Cavendish is that he actually independently did everything about electrodynamics before everybody else. So we could have Cavendish's law for most of the things that you will learn here. However, history has somehow forgotten Cavendish. We don't have, well, there's Cavendish labs in Cambridge, but we don't have the Cavendish law. And this is utterly unfair because, you know, a solid 12 years before Coulomb, he did a much better experiment, Coulomb, at determining the exponent of the force. We'll discuss that a little bit. And why was Cavendish not entirely forgotten? Well, it's mostly due to James Clerk Maxwell, who actually published a book after discovering the lab notes of Cavendish and realizing just how absolutely revolutionary this guy's work was. This book is again available electronically, and I give you the link on the Canvas page. It's or somewhere in the lecture notes maybe. But you can find this book and just go see what it is. So let's just talk a little bit about that. So what was the idea of Cavendish's experiment? It's actually an experiment that you can relatively easily do at home if you've got some basic metalworking skills. So the idea is that the 1 over r square form of the law has one very, very important consequence if it's exact. It means that if you have a uniformly charged spherical object, then there's no force inside. Absolutely no force inside. And this is only true if the law is 1 over r squared. Any deviation from that can be ascribed either to a photon mass or to a different exponent in the law. So what did Cavendish do? He had 2 concentric shells, and he was able to control the charge on the inner shell through a tiny little charging device here that he could remove, and then he could do the experiment, discharge the thing, and then disassemble, and then remeasure the charge. So that gave him a limit on the possible deviations for the r square law. And once again, he got it to about 1 part in 50. So I think his result was 2.02. Okay, which is pretty good. But it's an experimental fact. Later, Coulomb did another experiment with these torsion balances, which is also a smart idea. But actually, this is better. Yeah. So we give a lot of credit to Coulomb, but not enough to Cavendish. That said, this is still really funky, fun physics. There have been big developments on this over the last few decades. 1971, the year of my birth. Yeah, I'm that old. There was this very famous experiment by Williams, Fowler, and Hill that used essentially a glorification. I think I have an illustration. Used a glorification of the ideas of Cavendish in order to do the same thing, but now with actually dynamical charges and a kind of special shape with lots of controls on it. So they were able to get a kind of much more accurate determination to this. So the deviation, if the exponent is 2 plus epsilon, then they would say that the epsilon is now of the order of 10 to the minus 16. Okay, so if you know how slowly logarithms grow, you can ask yourself what this represents even for the electrostatic influence of charge here to another one in the Andromeda galaxy. Okay, so these deviations are absolutely tiny. Still, finding a deviation would require a revision of everything we know about the fundamentals of electrodynamics. So this is still current research because there are people who are trying to test these things in more intelligent, more modern ways. Each time new experimental methods are devised, one of the first things that people do is try to apply it to these very, very important problems of answering these fundamental questions, whether these 4 aspects that we discussed earlier are correct. Okay? So just a few more details. Sorry, I'm getting enthusiastic about these things, but I should accelerate a bit. One thing here I want to say, so kind of related tests are tests of the photon mass. So here, what can you do? Well, one of the consequences of photon mass would be that the group velocity of light excitation would actually depend on the frequency of the light, right? Because light would have like an m0. And then you do m0 squared plus k squared square root. That would be your energy. And then you differentiate that with respect to k to get the group velocity. But that would depend then on the frequency. So no deviations found. You can more interestingly look at distant astronomical sources to see whether, for example, you can correlate the arrival time of particular fluctuations in the light fields that you get there. Because if they have different frequency and they travel at different speeds, then essentially you would maybe observe some correlation of noise, and then a couple of seconds later, you'd get the same correlation pattern, but at a different frequency. And then you'd see, oh shit, there's a problem here. But no, again, no. Lots of lab tests of Coulomb's law that we've discussed about. Interestingly, so a person that you've encountered before, something to do with cats again, Schrödinger said, let's not do anything complicated here. He actually suggested a measurement which essentially, I think, still competes as one of the most accurate determinations of the absence of Coulomb of photon mass. Essentially, the idea is that you say, okay, well, we need a big sphere to have accurate measurements. So where's the closest big sphere? It's the Earth. You just measure the magnetic field around the Earth. That's it. And then you kind of look whether it obeys the condition that there is no magnetic charge. You check that the flux is 0. And if the flux isn't 0, there's something wrong, because that would mean that there would be a magnetic charge. And the absence of magnetic charge means all these extra consequences related to this. Okay, so still today you can do that. But these days it's more fancy because you can do the same idea in lots of different places. For example, around Jupiter. Okay? So you can do the same trick with Jupiter, where you kind of you measure the fields around that and you see how it is. However, even these lab-based modern versions of either Cavendish's idea or Coulomb's torsion ideas are again like competing with all of this. I think you have to take all these numbers with a bit of a grain of salt here. I kind of always find it quite amazing what they have. This is, after all, kind of determination of inaccuracies on these things. So maybe it's a bit different, but still, I mean, these are accuracies for things which you're not going to find in most other walks of life. Certainly, for example, if you look at the timetable of the Nederlandse Spoorwegen, you will get nowhere near 10 to the minus 50 accuracy. So you should be admirative of the work of those people here. Okay. Other kind of completely mind-boggling things about charge that are essentially inessential for electrodynamics, like we will study it, however, remain experimental facts as far as we can see. Well, when we describe an electron, we say it's a point particle. Now, I don't know if you sleep at night And quite frankly, I don't know how you can, yeah, because what's your picture of an electron? Does it have a size? If it has a size, that's okay, but how do you determine it? How big is it? What consequences does that have? Yeah. If it has no size, if it is a point particle, then what is it? How can you sleep at night? I don't get it. Huh? So, you know, what's the problem? Well, if it is a point particle, then essentially, as we'll see later, and I think you've seen this equation in the past anyway, you know that the energy can be viewed as being contained in the electromagnetic fields. And in the vicinity of an electron, the electric field just diverges, right? And the volume integral of the square of the electric field does not converge. That goes to infinity as I let the radius of the electron to 0. So these electrons, we see they have a finite mass, but I'm telling you that there's infinite energy in the field, and you know, energy has mass. So how do you sleep at night? My question. Okay. So people have thought of alternatives, and again, heroes of the past have thought creatively about this. So let's just do the supposition that indeed the electron has a finite radius. Fine, the energy is finite, it's very large, but it's finite, so less worry somehow, sleep better. But more interestingly, this would give an explanation for the origin of inertial mass. Okay, how many of you did know about this? Cool fact, mass from electrostatics. You thought you were going to learn Gauss's law and things like that. I'm talking to you about mass here. So, okay, so what's the idea? Let's model the electron as a uniformly charged shell and ask how that works if we try to accelerate it. Okay, we're actually not going to do much electrodynamics of accelerated charges. That's going to be for the next course where you study radiation, that sort of thing. We'll hint at all these things. However, it's kind of intuitively clear that if you have a uniformly charged shell and you start trying to move it, there are going to be retardation effects. The field that is felt by different points on the shell is different, depending on the direction that you're giving. And if you look at the forces that are acting on these things, you find that there's a resulting component going against the acceleration vector that you're trying to impart. Okay? Yes?
I don't understand how you can even think about modeling classically a quantum object.
They didn't know quantum mechanics back then when they were worrying about that. So they started worrying about the energy content first. So this was in the days even before quantum mechanics. Quantum mechanics does not help with any of this, but of course would make any maybe first principles modelization of that thing complete nonsense, because you see this modelization here puts a lot of stuff under the carpet. What's the shell made of? How does it hold the charge? What are the charges that are in there? And if I know already from Millikan that my total charge has to be a multiple of this integer stuff, and you're telling me it's not distributed, why can't I just cut it in 2 and get half? You know, so all these things don't add up. However, the observation is that if we develop this kind of Greek mythology model of an electron as a uniform shell, that we get mass for free. Okay, so great names, you know, Thomson, Heaviside, Lorentz, Poincaré, Fermi, Wilson. All these people thought about this, and people in the future will return to this as well. Okay, it's not completely closed. Of course, these days we've got the, you know it as the Higgs mechanism, developed by Phil Anderson, yeah, famous matter physicist, which was cited actually by Higgs in this. But there's a different origin for these things, but still electromagnetic mass is like a super stimulating idea back then. Okay, so now maybe just to carry on with where we were, almost finish on this as well. What about linear superposition? Okay, so wouldn't it be cool if indeed we had an experiment where we put charge so close together that the fields would become so large that at some point some different law would kind of take over? Maybe the true equations of electrodynamics have these little nonlinear terms that indeed mean that you can only, for example, stack that much energy in a certain region of space. Afterwards, if you try, then there's a kind of resistance, there's a kind of rigidity to it that prevents you from doing that. Nothing ever found that goes in that direction. So there are very famous attempts, again, by theorists to build alternative theories involving nonlinear versions of electromagnetism. Again, mathematically, it doesn't have to be linear. It's just an experimental fact that it is. Okay, but mathematically, you can build up lots of stuff. And Bonn and Infeld, 1934, the very early days of quantum many-body theory, they kind of had some really interesting stuff here. It's really, really interesting once you've learned the kind of canonical theories to go read these things, because that's when you realize how research really works. In a sense, we train you to digest all the equations that we give you. But you hear from other people like, Feynman and all these other people, they say, you should always question what you have. So everything I say here, you should question. And maybe the most pleasant thing that could occur for me in my career as a teacher is if one day one of you kind of came back and said, one day you talked about this chap like Henry Cavendish, and he had that thing. And look at what I did, this thing. 30 years down the line, you came up with a different construction of that using maybe new constructions you can make with call that, I don't know what, you come up with it. But then you kind of give a few more decades of accuracy to these measurements. Yeah? That would be cool. So my point is that this whole thing is not a dead subject. It is not a closed subject. It is just an extremely beautifully coherent subject. It's an extremely beautifully converged subject, okay? But a bit like in theory of evolution, maybe you've read the books by Stephen Jay Gould and stuff, about punctuated equilibrium. Things move fast and then they stabilize for a long time on something, and then they go to another equilibrium again. Maybe we're just in a kind of steady state phase here, where one day we'll throw all of this out because there will be some nonlinearity found out for one reason or another, and we'll have to change Maxwell's equations, Einstein's relativity, their relationship to quantum mechanics, all these things. So until then, it's important that we make best efforts to really make sure experimentally that all the things we're going to build are actually correct. But stop being bored by Coulomb's law, because, quite frankly, it might actually be one of the most consequential fields of research that exists in physics. Because if we were to find a deviation to this, we would have to revise absolutely everything, including everything we think of about the evolution of the universe and whatnot. Yeah? And in fact, also almost everything we know, a few years ago, everything we knew about the universe was communicated to us from electromagnetic radiation. These days, you've got gravitational waves, but that's it. Yeah. Next time, we'll get down to business. Okay. Thank you.